We are continuing to look at multivariable regression. So multivariable regression is when you have more than one predictor variable. That's the independent variable used to predict something else. And we are looking at generalized linear models. So underlying, they have a linear relationship between the variables, but it depends on what you're trying to predict as to which type of model you use. So the logistic regression, or logit, we looked at in the previous video, helps to predict whether something is or isn't a particular event. And so it does focus on the probability of the event occurring. In this particular video, we're going to look at Poisson regression, which looks at counts. So can we predict the number where the number is an integer, a whole number? And in the video after this, we'll look at linear regression, where we are looking at measurements. So we're looking at multiple variable regression, where we are focusing on the impact that the coefficient or that the variables are having, that these predictor variables, what impact are they having on that outcome variable or dependent variable. So just a reminder, we are at drstephpowers.github.io/BIA, and we are here under regression, under prescriptive analytics, because we are focusing on the impact those variables have on that dependent variable, so that we better understand if we change what's happening with those independent variables, then we can change what's going to happen to that outcome variable. So let's look, for example, at a Poisson regression example. So click here on regression. It'll take you into GitHub. Click on open in Google Colab, log in, save a copy. That lets you work through the workbook with us. So let's take a look then. All right, so we're here in Poisson regression. We're using a data set from Gelman, 2007. And this one is about the New York City Police Department stop and frisk policy. So here you are pulling in from a URL. It is going to it's going to come in as a CSV file. So we need to know that we're going to skip these couple rows and that there's spaces separating the information. So another way to pull in data, different from the previous methods we have used. Remember, we have looked at importing CSV and Excel files from your own Google Drive. We've looked at pulling in data sets like we did with the penguins in the previous one, where it is from it's built into a Python package. Now we're looking at how do you bring one in that's posted on the internet. All right, so here we are. We're going to use linear model from sklearn, and we're doing Poisson regression. So we need Poisson regressor. And we're going to do train test split to help divide up the data so that we can see how well the model works by using our test data versus what our regression model predicts for our values. So we're pulling in this Gelman data set, and the data set contains the following variables. It contains stops, the number of police stops between 1998 and 1999. We're going to try to predict the number of stops with our regression model. So that stops is counts. They're whole numbers, right? So that's why we're using the Poisson model. There are different variables here. There are the number of arrests that took place in 1997 for each combination of precinct, ethnicity, and type of crime. We have an identifier, a nominal variable that is the precinct number between 1 and 75. We have a nominal variable of ethnicity, and so it is currently coded 1 for Black, 2 for Hispanic, 3 for white. And then we have a nominal variable for the type of crime, violent, weapons, property, drugs. So if we want to look at the data set itself, when we brought it in, we called it frisk as a CSV. And so we can look at it here by calling frisk. So what I do is create a Poisson regression model to try to determine the number of stops based on some of these variables. Now, when you are doing regression models, you need to do one-hot encoding. One-hot encoding is where we take nominal variables and we turn them into binary. So we can't use a variable that says Black 1, Hispanic 2, white 3. We have to separate it out and create a column that is Black, a column that is Hispanic, a column that is white. You cannot use all 3 of them in your regression model, because when you include all 3, they are highly correlated, right? That's that multicollinearity that we talked about in the previous video. So that's because when you include all three, what you get is that if someone is not Black and not Hispanic in those two columns, then they're going to be white because that's the only option in this particular data set here. So they're highly related, right? Because if you have 2 out of the 3 columns, you can predict the numbers in the third column. Which means if you are going to include multiple variables related to ethnicity, you can't include more than 2 out of the 3, right? You have to leave at least one out of the model. Otherwise, all of your variables are highly correlated. So same thing here with crime. If we wanted to include multiple variables related to crime, there are 4 variables. We do one hot encoding. So we create a column called violent, a column called weapons, a column called property, and one called drugs. 1 if it is that, 0 if it's not. But you can include all 4 variables in the regression model because they're highly correlated. So you need to pick a subset for building your model. So let's start out here by taking and creating a new variable called Black. And what we're going to do is we're going to use methods that we've used before, which is we're going to make a copy of the column called ethnicity. We're going to call it Black. And then we're going to take, remember that ethnicity, if it was 1, it was Black. If it was 2, it was Hispanic. And 3, it was white. So for this new column, we're going to turn the number 2 into a 0 and the number 3 into a 0. So we simply have a column, a variable that is 1 for Black and 0 for everything else. So we're going to create that new one here. Okay. Let's create a model, let's say, that is Black and drugs. Right? So what we hear in the news is people are more likely to be stopped and frisked if they are of African American descent, as well as if it is a drug-related crime. So let's see if that would predict the number of stops. So we're going to have our variable Black, and then we're going to have our variable drug. So we're going to make a copy of the column called crime, and we are going to make it so that, let's go back, if it's violent, it's 0, weapons is 0, property is 0, and we'll make drugs 1. Okay, so creating a new column here, that's what this replace tells us that we are changing the 4 to a 1, changing everything else to a 0. So now we have 2 columns here that we'll use in our model. So we're going to separate out the data into training and testing data, like we did in classification models. And this allows us, again, to test how well the model works. So what we're going to do is we're going to take the variables Black and drug, and we're going to try to predict stops. We're going to do a test size equals 0.2, so 80% in the training data, 20% in the test data. Notice in this case, we don't have a stratify. We use that stratify when we have classifications where we have penguin, not penguin, to make sure that it's represented in both the testing and the training data set. When you get to continuous variables, discrete variables, then what we want to do is we'll just leave it because there's a lot of variety in the data. And so that's automatically going to be in the test and train. So you can't really make sure that there's certain numbers in the testing or training. So see, stratified has disappeared. All right. So what we're going to do is we're going to call the model, fit the model, and then find the coefficients because, again, we are focusing on these variables. Can we use whether someone is African American, whether someone is being accused of drug-related crimes? Does that impact the number of stops? Okay. All right. So call the model, Poisson Regression. Fit the model with our training data. Again, you can combine these two together by putting .fit here at the end if you want. Depends on how efficient you want to be with your code. The focus here is to call our coefficients and our intercept. The way that Poisson works is the average observed count, our lambda, is equal to e to the power of, and then you have this intercept plus the first coefficient times whatever our first variable is, whether or not they are Black, and then the plus the second coefficient times our second variable, whether or not it is a drug crime. Okay, so how would we interpret this information? Well, in a previous run, I got that the intercept was 4.8044. Again, because we're not using a random state when we do our test train, it's possible that you can have different data in your testing and training, which will impact the model, right? So you might get slightly different numbers. So here we can see the intercept is 4.82. So what does this mean? It means the average number of stops is E. Let's pull up our calculator here. Okay, E to the 4. It was 8044, but in this case it's 8211. Okay, so in this particular run, what we find is that the average number of stops is 124. When I did it previously, it's 122. Okay, so that's what you get from the intercept. We take E to the intercept and we get the average number of stops. All right, now what is the impact of our two variables? So here we have our coefficient of 0.8379. So we're going to take E to the power of 0.8379 for however many places you want to go. We get 2.3316. So what does this mean? This means that if you identify as Black, then you have a 2.31, or in the previous version, 2.16 times more stops. Sorry, you have 2.31 times more stops than non-Blacks. So what we're seeing here is that being Black does increase the number of stops. And the impact here is 2.3 times that. Okay. The other variable, so our second coefficient here is a negative 0.92. So we would take E to the power of 0.922888862. And that is a negative number, so we put a negative on that. And we get 0.397 or 0.4. So what this tells us at 0.4 is that drug crimes are associated with a 60% less stops. Okay, so comparing it to 1, drugs are associated with 60% less stops than other types of crime. So we could look at the other types of crime. Maybe they are more likely to indicate what would increase the number of stops. Now, in terms of this particular method, we can get these coefficients. We can also predict the values with our test data. We have to compare the test and the prediction. We are going to have to convert it using 2numpy. And that allows us then to subtract the predicted and the test to get the error. So remember, our measurement error is the difference between the actual number and the predicted number. And what we should see is we should see an average error that is 0. We want a model that truly represents the variability in the data, which means we should have some predictions that are higher, some predictions that are lower. So then on average, the error should be 0. We can already see that there's going to be an issue with this model because the error is not 0 when we look at the average. It's 27.33. And we can plot this using matplotlib.pyplot as PLT. So we're going to plot this error we just calculated. You can call it residuals. You can call it measurement error. In fact, we're going to look at, I got a slide somewhere here. These words are very much interchangeable. So depending on if you come from stats, if you come from business, if you come from computer programming, you probably use different words. So in stats, we call them residuals. What is left over after the model? In business, we call it a measurement error. What's the difference between our predicted and our actual? If you are creating machine learning, so you are more computer programming, computer science, you call these cost functions or loss functions. These are all ways to measure the difference between what you predicted and what the number actually was. So you can use whichever terms you want. So what we're going to do is here we're going to plot the residuals, or the measurement error, which is just this difference between predicted and test. And here we're going to put a dark black line here at 0, because remember the goal is to hover around above and below 0 to be a random scatter. We're looking for error that is a random scatter around 0. If we have too much error that is all just above or below, or we see a pattern in the error, then we have an issue with the model. If we see a pattern in the error, then it's not the right kind of model. If we see that it is shifted, so if in this case the average was up here, we see that there's some random ones that are way off, we're probably missing some good predictor variables in our model. So we can see that, just with the two variables we've chosen, it's probably not a very good model. So let's dive deeper. Remember, what we really want to do is we want to know if these variables, because we've just said, here's the average number of stops. If you're black, you're more likely to be stopped. So there's more times the stops. Drug crimes, less so. What we want to know is, are these variables really statistically significant? Do we have all the variables needed to explain the difference in the number of stops? So to do that, what we actually need is the statsmodel.api as SM, import statsmodel.api as SM. And then what we're going to do is we are going to use GLM, so it's a generalized linear model like we talked about, from that stats model package. We're going to use our training data. So Y train, X train, we haven't re-rolled it. It's the same data as before. And then we're specifying that the statistical model we're using is in the Poisson family. So we call the model, we fit the model. Sometimes I write it as one line, sometimes I write it as two. You can do either one. So what we're going to do is we're going to do that Poisson model in the stats model app because it gives us this summary. So we'll call a summary here. And what we see here is that we have this pseudo R squared. The pseudo R squared is very tiny. Okay. And so what does this tell us? This tells us that yes, being black, have a crime be drug, they are statistically significant. They are important variables for predicting the number of stops, but they don't explain a whole lot of the variability. Now, that of course is because we have count data and we simply have a binary classification of you are black or not, you are investigated for drugs or not. And so of course binary nominal variables don't have the same level of variability as say counts do, right? So what we need is some additional variables here to help improve the model and the accuracy of the model, because right now that model is not accurate at all, but these two variables do explain some of the variability. So why don't you try, add some additional variables and see if you can improve the model. Now remember that you're using one-hot encoding, so you're taking these variables and you are turning them into binary, and that you can't include all of them. So for example, we could create a new model where we add, so we go through and we add a column. Let's call that column, we could add a column for Hispanic, we could add a column for weapons, and we could add those two to the model to see if the model improves. So take a moment and give that a try. So we can create another model where we've added Hispanic and weapons. And so you can see we've added a new column here called Hispanic. That is doing our one-hot encoding here, where the second option in the original data set here for ethnicity, Hispanic is 2. So we'll make the 2 be a 1 and the rest be 0, creates our new variable here. We could also add weapons, so we're doing the same thing. We copy the variable crime over and we add a column called weapons, and weapons was the second one in the crime categories, so we'll make it 1 and make the rest 0. So we now have 4 variables in our model, so we'll do a train test split. We are going to do black drug, Hispanic weapon, and then try to predict the number of stops. We repeat that process, or we do that process by calling the model, fitting the model, and then we get new coefficients. And so the interpretation of those coefficients is the same. We're going to take e to the whatever those numbers are, and that will tell us whether or not being Hispanic, it increases the number of times of stops, whether weapons crimes increases the number of stops. So notice in this case, the coefficients here are all positive except for 1. And so only drug crimes seem to reduce the likelihood of stops. The rest are increasing it. And then it simply becomes a matter of how much is that increase. And so if you have a number that is bigger, then it is going to, so let's just pull the calculator up here. Let's look at, so we have e to the power of 1.3038. And so our first variable here, black, if we include the other variables here, then this says that being black means that you are 3.68 more times likely to be stopped. And if we compare that to Hispanic, where we have e to the 0.839, gotta make sure that's the third one I put in. Yeah, okay, 839. Then if you are Hispanic, you are 2.3 times more likely to be stopped. Notice that the intercept changed. So the average observed count is now e to the 4.03. And that's because now what we're looking at is that the average is now a different baseline that gets adjusted for both whether an individual is Hispanic or whether an individual is Black. So that average observed count is kind of that base that we're then adjusting based on certain conditions. Now, if we look at with our stats model, so statsmodel.api is SM, and we take that same training data and we fit it, and then we do a summary, what we find is that all 4 variables are statistically significant. Our pseudo R squared is still very tiny. In fact, it's a negative number, very close to 0. We're still not explaining a whole lot of the stops. And so additional variables would be warranted to better predict the number of stops.